Partial derivatives are the move where multivariable calculus stops being scary. Up to this point in the playlist, we have stacked up machinery, functions of several variables, vectors, limits in higher dimensions. None of that was calculus. Today, that changes. We get the curly D symbol, a bit of its 18th century history, the surprisingly elegant fact that mixed partial derivatives commute, and a stack of worked examples until the procedure feels boring. Which is the point. Once it's boring, it's automatic, and we can stop thinking about it. In single variable calculus, the input is a number on a line. There is exactly one direction you can nudge it, left or right, so one derivative tells you everything about the rate of change. In multivariable calculus, the input is a point in a plane, or in 3-space, or higher. From that point, you can walk off in any direction at all, and the function will change at different rates depending on which way you went. That's a problem. There is no single number that captures the rate of change anymore. The partial derivative is the first, simplest response to this problem. It refuses to deal with all possible directions at once, and instead asks a much narrower question: if I shove the x-coordinate of my input and refuse to touch anything else, how fast does the function respond? And honestly, that's it. Everything else in this video is bookkeeping on top of that one move. Here is the move that makes partial differentiation easy in practice. Take z equals f of x and y, freeze the y-coordinate at some specific number y0. Once y is frozen, it isn't really a variable anymore, it's a constant, and f of x comma y0 is just a single variable function in x. We already know how to differentiate those, so we do. The ordinary derivative of that single variable function, with respect to x, evaluated at x equals x0, is the partial of f with respect to x at the point x0, y0. So every other variable becomes a constant for the duration of the calculation. It can still appear in the formula. It just doesn't contribute anything when we differentiate, because constants have derivative 0. The formal definition uses the same limit machinery you saw in single variable calculus. The partial of f with respect to x at the point a comma b is the limit, as h tends to 0, of f of a plus h comma b minus f of a comma b all over h. Look at what is moving in that expression and what is not. The first coordinate gets perturbed from a to a plus h, and then h gets squeezed down to 0. The second coordinate, b, just sits there. That's where the word partial comes from. Most of the variables aren't going anywhere. For the partial with respect to y, you do the mirror image, perturb the second coordinate, hold the first, take the limit. The same template works in 3 variables, in 10, and 100. You always pick one coordinate to vary and pin everything else. Quick history note on the funny-looking d. I love this story, honestly. That symbol with the curl on the back is called the partial d, and it carries one piece of information. Only one variable is being differentiated here, and the others are along for the ride. Adrien-Marie Legendre is the first person to use a symbol distinct from regular d consistently in 1786. He was tired of confusing partial derivatives with full differentials in his own notes. The modern shape of the symbol, and the convention of using it everywhere, comes from Carl Gustav Jacob Jacobi in the 1840s in his work on the calculus of variations and on what we now call Jacobian determinants. Before any of that, people wrote a plain d for both kinds of derivatives and had to track in their head which variables were being held fixed at any given step. Which sounds minor, and it isn't. Every time you write the partial sign, you're sending a signal to your reader and to your own future self about what is moving and what is locked. Time to draw this. The graph of z equals f of x and y is a surface sitting above the xy plane. Take a vertical plane, y equals b, parallel to the xz plane, and use it to slice the surface. What you get is a curve. A one-dimensional object living inside that plane, described by z equals f of x comma b. Since y is pinned at b on this slice, the curve depends only on x, and the partial derivative of f with respect to x at the point a comma b is exactly the slope of the tangent line to this curve, at the point where x equals a. The partial with respect to y is the mirror image. Slice the surface with the plane x equals a, get another curve, take its tangent slope. 2 slices, 2 slopes, one for each direction you could walk away from the point. One time, by hand, from the limit definition. After this, we get to use shortcuts, but I want to do this once so we know what the shortcuts are actually doing. Take f of x and y equals x squared plus x times y. The target is the partial with respect to x at the point 1, 2. By definition, that is the limit as h goes to 0 of f of 1 plus h, 2 minus f of 1, 2, all divided by h plug in. The first term, f of 1 plus h, 2, square 1 plus h to get 1 plus 2h plus h squared. The second piece, 1 plus h times 2, expands to 2 plus 2h. Add 3 plus 4h plus h squared. Now the other piece, f of 1, 2, that is 1 squared plus 1 times 2, which is 3. The subtraction kills the constant 3. The numerator collapses to 4h plus h squared. Pull out an h and divide it through. The difference quotient is just 4 plus h. Let h go to 0, and the answer is 4. The partial is 4. Sanity check with the rule we are about to start using everywhere. Partial of f with respect to x, treating y as a constant, is 2x plus y. At 1, 2, that is 2 plus 2, which is 4. Same answer. The shortcut works because the limit works, not the other way around. Take f of x and y equals x squared y, plus 3xy squared. For the partial with respect to x, y is now a constant. Differentiate term by term. The first term, x squared times a constant y, becomes 2xy. The second term, 3y squared times x, has the constant 3y squared pulled out front, leaving the derivative of x, which is 1, so that term contributes 3y squared. Sum them, the partial of f with respect to x is 2xy plus 3y squared. Flip everything around for the partial with respect to y. Now x is the constant. The first term, x squared times y, has x squared in front and the derivative of y, which is 1. That's x squared. The second term, 3x times y squared, has the 3x pulled out and the derivative of y squared, which is 2y, combining to give 6xy. Sum x squared plus 6xy. Every line of that was a one-variable derivative. Different letter, same calculus you already know. The chain rule shows up exactly as you would expect. Let f of x and y equal the natural log of x squared plus y squared. For the partial with respect to x, the outside function is logarithm. Its derivative is 1 over the argument. Then we multiply by the partial of the inside. The inside is x squared plus y squared. Treating y as a constant, its partial with respect to x is 2x. So the partial of f with respect to x comes out to 2x over x squared plus y squared. Identical logic for y gives 2y over x squared plus y squared. Now plug in the point 1, 2. The denominator becomes 1 squared plus 2 squared, which is 5. The partial with respect to x is 2/5. The partial with respect to y is 4/5. And these are slopes. Pick a direction, and the surface tilts that much. One annoying fact about partial derivatives is that the same object has half a dozen names depending on whose textbook you opened. The clean mathematician's notation is partial f over partial x. The same thing also turns up as f sub x, or as partial sub xf. Older books and some software systems use d sub 1f to mean the partial in the first argument. All of these are the same object. There is also an evaluate at a point notation, a vertical bar with a point written below it. That's just a different way of writing what you'd otherwise put in parentheses. The one really worth flagging is the physics convention. If you pick up a thermodynamics book and see a parenthesized partial of f with respect to x with a little y written as a subscript outside the parens, that y is the variable being held fixed. Physicists do this because in thermodynamics it isn't always obvious which variables are the independent ones, so they spell it out. You don't need that for ordinary math, but it won't trip you up if you can read it. Pick whichever notation feels nicest for your own work and learn to recognize the rest. A partial derivative is itself a function of the same variables, so we can differentiate it again and get second-order partials. For a function of two variables, there are 4 of them. 2 pure second partials, differentiate with respect to x twice, or differentiate with respect to y twice, and 2 mixed partials where you take x then y, or y then x. The notation needs a warning. The convention is to read the denominator inside out, or equivalently right to left. Partial squared f over partial y, partial x means do partial with respect to x first, and then partial with respect to y. You'd think the order of differentiation ought to matter. And here's the punchline, for any function you'll ever actually write down, it doesn't. This is one of the genuinely beautiful results in multivariable calculus. If the second partial derivatives of f are continuous in some neighborhood of a point, then the 2 mixed partials at that point are equal. The partial with respect to x then y equals the partial with respect to y then x. Stated by the French mathematician Alexis Clairaut in 1740, and given a rigorous modern proof by Hermann Schwarz in 1873, which is why German tradition textbooks sometimes call it Schwarz's theorem. The continuity hypothesis is mild. It holds for every elementary function on its domain, but it's not automatic. There is a famous counterexample where the mixed partials exist at the origin but are unequal, because they fail to be continuous there. For real calculations on real functions, you can use Clairaut without a second thought. Let's verify Clairaut on something concrete. I always found this kind of thing more convincing than the proof. Take f equals x squared times y cubed, try x then y first. Differentiating with respect to x, treating y cubed as a constant, gives 2xy cubed. Then differentiate that with respect to y. 2x is now constant, and the derivative of y cubed is 3y squared. The product is 6xy squared. Other order. Partial with respect to y first, x squared is constant. Derivative of y cubed gives 3y squared, so we have 3x squared y squared. Differentiate that with respect to x, 3y squared is constant. Derivative of x squared is 2x, product is 6xy squared. Identical, 6xy squared either direction. Clairaut works on every polynomial, every elementary function, every smooth function you will ever meet in practice. Do this once in the open and you'll trust it forever. Nothing about partials cares whether you have two variables or 200. To prove the point, here is 1 and 3. Let f of x, y, z equal x times e to the yz. Compute all three first partials. Partial with respect to x, y, and z are constants, so e to the yz is just a number. The derivative of x times that number with respect to x is the number itself, e to the yz. Partial with respect to y, now x and z are the constants. The x in front rides along. The e to the yz gets the chain rule applied. Its derivative with respect to y is z times e to the yz, because the derivative of yz with respect to y is just z. Multiply by the x out front and you get xz times e to the yz. Partial with respect to z is the same calculation with the roles of y and z swapped, giving xy times e to the yz. 3 variables, 0 new ideas. Same recipe as before, and yes, it keeps working in 10 variables or 100. So why a whole video on what is, computationally, just single variable differentiation with the other letters treated as constants? Because nearly every other object in multivariable calculus is built from partial derivatives. The gradient is just the vector you get by collecting all the partials and stacking them, and it ends up pointing in the direction of steepest ascent. The directional derivative, the rate of change in any chosen direction, is a linear combination of partials. The multivariable chain rule is partials all the way down. The Jacobian matrix that you'll meet when you start changing variables in double and triple integrals is a matrix of partials, and its determinant tells you how volumes deform under the change. And then there is physics. The equations that govern almost everything continuous are partial differential equations: heat flow in a metal bar, vibrations on a string, light, electric potential, gravitational potential, quantum mechanics. They are statements relating partial derivatives of some unknown function to one another. The heat equation, the wave equation, Laplace's equation, Schrödinger's equation, all expressions in the same partial derivative we just computed by hand. You don't need to know any of them yet. The calculation we just did on the toy polynomial is the same calculation you'll keep doing for the rest of this subject. Here is everything in one place. A partial derivative just promotes one variable and treats the rest like numbers. Then it's a regular derivative. Formally, that is a difference quotient where only one coordinate gets perturbed. Geometrically, it is the slope of a slice through the graph, taken parallel to one of the coordinate planes. The notation is the curly d, standardized by Jacobi in the 1840s on top of earlier work by Legendre. Physicists may also hang a subscript on the outside to spell out which variables are pinned. We did one partial from the limit definition just to pay the bill, then used the shortcut rule on everything else. Clairaut's theorem says that for well-behaved functions, mixed partials commute. 3 variables look exactly like 2, and partials are the building blocks of the gradient, the directional derivative, the chain rule, the Jacobian, and every partial differential equation in physics. Next time we bundle the partial derivatives into a single vector, the gradient, and use it to measure rates of change in any direction at all, not just along the coordinate axes. A partial derivative tells you what happens when one variable changes while the others hold still. This channel, similarly, gets one variable better at a time. Your likes and comments are what move it. If you got something out of this, please like the video, drop a comment with what clicked for you, or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.